So as we know, magma consists of more than nine oxides. So in geology, oxides are considered as components. So it is a multi-component thing. So we cannot study the crystallization behavior in the multi-component system. So that's why we simplify that with bicomponent, tricomponent, or unicomponent. So we'll start from bicomponent magma. Crystallization behavior of bicomponent magma. So magma that consists of a two components, or you can see two minerals. Generally, here we are considering two minerals, but there are two components. So magma consists of two components, which that is bicomponent. So if they are consist of two components, so there are different relationship between components. According to the crystallization behavior, will be shown by the magma. So there are different relationships. What are they? One, the eutectic. Peritectic. Fast case, in the eutectic magma, where the two components they will not affect each other during crystallization. They will only mixable at a particular composition. So in case of peritectic, crystallization of one component will be affected by other, and also in solid solution they will always form a mixture of solid. Any type of crystallization they will form always a mixture of solid. So we'll start from eutectic crystallization behavior. So all in this case, all bicomponent magma follow one rule, that is the main principle where the melting temperature of one component is affected by the presence of other component. If we are considering a single component, suppose we are considering a mineral A, it has a melting temperature of 1000 degree, melting temperature or freezing temperature 1000 degree. Then that means कि when 1000 degree temperature will reach, it will start to crystallize. देखो crystallize करना start हो. But when you add some amount of B with a component, then suppose B has a melting temperature of 1200 degree. So the amount or extent we are adding with A, how much B we are adding with A, according to that the melting temperature will decrease. So the main principle which is the presence of one component will affect the melting temperature of other component, depending upon which component is dominant. To the dominant also. So that dominancy depend upon a composition that we will study here. So there are different magma, bicomponent magma. They are showing eutectic relationship. So we will study that diopside anorthite. So diopside anorthite, two minerals, they will show eutectic relationship. Also your orthoclase and quartz, they also show eutectic relationship. So all these crystallization behavior are represented by TX diagram, or you can say phase diagram. So the T stands for temperature, X stands for composition. All these are drawn also in isobaric condition. One atmospheric pressure. All these phase diagrams are isobaric. So if you change the pressure, then the figure will change or the phase diagram will change. This is the Eutectic phase diagram where we are taking two components, diapside and anorthite. So it is CmGSI 206 pyroxene. It is plagioclase Ca2Si2O8. This diagram is separated into three field. One is liquid field, another for liquid plus solid, and solid field. They all depend upon the temperature condition. They depend upon the temperature condition and depend upon the composition also. So at what composition and what temperature the magma will be in solid, or will be in solid plus liquid condition, or completely in solid condition. So just an example, you can take this. Suppose if this is a composition. At this temperature, it will be completely liquid. At this temperature, it will be solid plus liquid. At this temperature, it will be completely solid. So how a bicomponent liquid or magma crystallizes, that will study through this diagram. So it is a phase diagram. Here we are taking composition. This is diapside, which is 100% at this point, and 0 at anorthite end. And anorthite, it is 100 here and 0 at this end. So the melting temperature of diapside is 1392 degree, and the melting temperature of anorthite is 1553 degree. So now we will take a composition, then we'll show how that will crystallize with a falling temperature or in a slow cooling rate. That is we call equilibrium condition. So first we will study what is the equilibrium crystallization behavior of eutectic magma. Equilibrium crystallization. Equilibrium means always a solid and liquid, they will be in equilibrium with each other. That means the slow cooling is going on. So the slow cooling hour talk. So we can take any point on the liquid field. So by applying lever rule, we can know the composition of that point. You can take any point. So just draw a perpendicular to the abscissa. It will toss this line here. So it will give a composition, that is will be some amount of diapside and some amount of anorthite. Suppose if you are taking this, if here is a point, so you will draw a vertical perpendicular to the abscissa. It will give that anorthite is 60%, diapside is 40%. So this is called as a lever rule. This is called as a lever rule. So we will take any liquid, then we will show how it will crystallize. So here we have taken a liquid at this point, then we are drawing a perpendicular to the abscissa. So it is given the composition that diapside is 82% and anorthite is 18%. So you can take also here. So all have the same crystallization behavior. So we will only take one. It is at a temperature of 1500 degrees centigrade. It is at a temperature of 1500 degree centigrade. So now we will change the temperature. We will decrease the temperature. Suppose now if this thing is here. So composition is moving downward with temperature. Moving downward with temperature. Suppose we have 1 liter of water. Okay, just one example. 1 liter of water. That means it is 100% liquid. 100% liquid. It is at a temperature of 15 degrees centigrade. So if you lower the temperature, when the temperature will fall, suppose temperature will fall to 8 degree, then what will happen? It will still in liquid condition. That means we have 100% liquid. Nothing will change until unless ki it will reach its melting temperature or freezing temperature. That is a 0 degree temperature. Suppose ki -1 degree temperature, ki 1 liter of water will not be completely water. It has some portion will be converted to ice. So now the composition will change. Now the composition will change. Similarly, here in case of bicomponent magma, this thing when reaches 1392 degrees here. So it is a before it is at initially we have taken ki it is at 1500 degree temperature. So now that we are decreasing the temperature, it is not crystallizing because still it is not reached to its freezing point. So the freezing point to pahunch. So when 1392 degree temperature will reach, that is the freezing temperature of dioxide. So now dioxide should crystallize. Will it crystallize there? Because dioxide, the melting temperature, that is 1392 degree, it is for pure dioxide. That is for 1392 degree, it is for pure dioxide. If you have a liquid or magma that only contain dioxide, then it will crystallize at 1392 degree. But now that we have added some anorthite to it, so that means ki its temperature will be lowered. Its temperature will be lowered. But you see that anorthite has a freezing temperature of 1553. So you have taken the composition here, dioxide 82, anorthite 18. So anorthite should be solid here because it is below 1553. But because of the presence of dioxide, it is still liquid condition. The dominant component is here dioxide. So according to that, the liquid, the melt will behave. So when it will reach to 1392 degree, it will not crystallize because now some amount of that anorthite will affect the dioxide. So the melting temperature of this mixture, that is dioxide 82 anorthite 18, will decrease. So how much will decrease? Just you take any composition, draw a perpendicular. When it will touch this line which we call liquidus, at that temperature it will start to crystallize. It will start to crystallize. So you don't have to calculate anything. Just draw a perpendicular. So it will touch the liquidus line. So at that point, that mixture will start to crystallize. Here also, it is touching the liquidus line here. So it will start to crystallize here. So from this point to this point, from this point to this point, there is no change in composition. That's why it is falling vertically. There is only change in temperature. Only change in temperature. That's why there is no change in composition. That's why it is falling vertically. Now that it is reaches at its freezing temperature, ये बताओ कौन सा freezing temperature reach करेगा. So when it is reached to its freezing temperature, now it will start to crystallize. That is the process. That nucleation, clustering, then some degree of supercooling. So at that point, you will not get any solid, but just below that temperature, it will start to form crystal. Crystal formation will start. Now the liquid is not 100% liquid. Now it has some solid and liquid. Now the composition of the liquid will change. Suppose before we have dioxide 82, anorthite 18, completely liquid. Now from that dioxide 82, anorthite 18, some will crystallize. So which one will crystallize? So dioxide will crystallize. So dioxide is the dominant component here. Dioxide will start to crystallize. That means that 82% of dioxide that present in the liquid, some of it will crystallize, some of it will become solid. Suppose we will take 82 gram of dioxide here and 18 gram of anorthite here. That means we don't have now, when it will reaches the freezing temperature, now we don't have 82 gram of liquid. Some of them will crystallize. Suppose now 5 gram of the dioxide is crystallized. So we have now 77 gram of dioxide. That means ki we cannot represent liquid here. It should shift. It should shift. It was 77 gram. Ho. Now 18 gram achi ka. Now 18 gram is another side. 77 gram your dioxide. If you represent it in percentage, then what will be the percentage of dioxide on another side? Suppose dioxide is 77. Dioxide is 77 gram, and another side is 18 gram. Now calculate what will be the percentage of dioxide and another side. Calculate कर दीजिए. Approximately कितना होगा?
81% is dioxide.
So before that, the dioxide was 82 before beginning of the crystallization. Now it is dioxide 81. So that means कि when dioxide percentage will decrease, it will go this, and also temperature is decreasing. So the resultant will be here like this. The dioxide composition will shift this way, temperature will shift this way, so the resultant will shift this way. But what is the percent of other side? 19%. So that means ki with progressive crystallization from that point, the percentage of the dioxide will decrease. The percentage of another side will increase. Only the percentage, but it will always remain 18 gram up to some point, no eutectic point. Up to the eutectic point, it will always remain 18 gram. But the percentage will increase because dioxide is removing from the milk. Now that it reaches here, a tiny crystal will form. So then it will follow this path. This path. Follow this path. So on this liquidoscope, when it is following this liquidoscope, solid will form. But the solid has a single composition, that is only dioxide. It always contain 100% dioxide unless until the eutectic point reached. So the bulk composition, if you are considering, how much percentage of liquid and how much percentage of solid. So we have taken 100% of liquid. In that liquid, you have dioxide 82 and another 18. Now, liquid is not 100%. So some amount of solids are already forming, that is dioxide. So at any point, we can calculate the how much percentage of solid and how much percentage of liquid within the magma. That is the bulk composition. So it is also a lever rule where the initial this line, it will divide the, this is called as tie line or a temperature line, you can say. It is divided into two segments. So this side segment is give the solid percentage. This side segment is give the liquid percentage. So how will calculate? This is initial composition. Initial composition is dioxide 82, anorthite 18. Then the composition of two ends. Then the composition at the two ends. So this is the point where our liquid is situated here. So you can just draw a perpendicular here, lever rule. So it will give the liquid composition. Okay, how much of dioxide and anorthite are in the liquid? Are in the liquid. So it is dioxide 72, anorthite 28%. Then at this end, dioxide is 100, anorthite is 0. These are the three compositions we have here. Just take the difference in composition. Just take the difference in composition between this point, and this point. The composition difference between this point and this point, it will give a liquid value of a liquid will be 18. You can take either dioxide or another. Anyone you can choose. The value of liquid will be here. Composition difference for liquid line will be 18, and composition difference between of solid line will be 8. 10. 10. So now you can calculate percentage of liquid by liquid plus solid into 100, solid by liquid plus solid into 100. Take the composition difference, apply this formula, they will get how much of liquid are formed and how much of solid are formed at any point on the liquidus curve. Understood? Now the liquid will progress on this path. So gradually the percentage of solid will increase and the percentage of liquid will decrease. So dioxide percentage will increase in solid, but dioxide percentage will decrease in liquid. Anorthite percentage will increase in liquid, but the amount will remain constant always. Up to this point, if you calculate, dioxide is always, sorry, anorthite is always suppose ki initially what we have taken, that much will be up to this point. Then when it will reaches this point, this is called as a eutectic point. This is called as a eutectic point where the temperature is 1274 degree. 1274 degree. So any liquid you will take, any liquid, they all will eventually evolve and achieve this composition. That is the behavior of a eutectic thing. All will evolve, all will modify, and will always achieve this composition. That is dioxide 58, anorthite 42. You take any composition of it. You take initially any composition, they all will come to this point. So eventually liquid will achieve a composition that is dioxide 58, anorthite 42. Dioxide 58, anorthite 42. When this composition reaches, now they both can simultaneously crystallize. Before that, any one of the component will crystallize, but when it will reach to the eutectic point, both simultaneously will crystallize. Both simultaneously will crystallize isothermally. Simultaneously crystallize isothermally. That means that there will be no change in temperature. There will be no change in temperature. So because during crystallization there are two crystals will form here, there will be two bonds will form here. So it will release a heat of crystallization. So the lowering of temperature will be adjusted by that heat of crystallization. That's why they are crystallizing isothermally. Otherwise, we can also explain it on the basis of phase rule, because here the degree of freedom will be 0. So any of the component should be consumed. Either solid will be consumed or liquid will be consumed to change the temperature. The liquid composition now reaches to 42 and at 58. So at this point, it will completely crystallize. The rest of the liquid, that is 42% of anorthite and 58% of dioxide, it will crystallize at this temperature, 1274 degree temperature. When all will crystallize, you will get dioxide 82, anorthite 18. Amount of solid or percentage of solid. That is, you have taken initially that much of liquid and you will get this much of solid. You can calculate this thing. If you have confusion, then just take dioxide 82, anorthite 18. These are initial composition. Just take 100 gram of liquid. We have taken 100 gram of liquid. Okay, 100 gram of liquid. Remember, we have taken 100 gram of liquid, of which 82 gram will be dioxide, 18 gram is anorthite. Okay. Another composition reaches here, so we can calculate the percent of solid and liquid formed up to this point. So you just use the lever rule here. Can use the lever rule here. So you will find that we have 43 gram of liquid and 57 gram of solid. Okay. From this point to this point, 57 gram of solid is found. That is only dioxide, and 43 gram of liquid is still left. So that 43 gram of liquid has 58% of dioxide and 42% of anorthite. So if dioxide is initially 82 gram, if it is 57 gram is already solidified, then how much is left? 82 minus 57. Without 25 gram. So if it is 25 gram, then how much anorthite is present? 18 gram. Understood? 18 gram. That means in this 43 gram of liquid, there is 25 gram is dioxide and 18 gram is anorthite. That means from this point to this point, there is no crystallization of anorthite. This point, at this point, all the liquid will crystallize. So all the 25 gram of the solid will liquid will crystallize dioxide and anorthite will crystallize. So before it was 57 gram already crystallized. So 25 plus 57, 82, and this 18 gram. So that means you have your solid here, that is dioxide 82, anorthite. So actually from this point, as it is crystallizing isothermally, that means temperature will not change, but the composition will change. So gradually it will shift to this point, so which will not show in the diagram. So we say that from this point it will isothermally crystallize and we will get our solid here. But it is key thing, this thing is happening here. This much of solid, this much of liquid is crystallizing. So as it is crystallizing isothermally, so that it is not changing. And another thing, Uchi, this is liquidous line. Okay, this is a solidus line. This line is solidus because above this always will find liquid plus solid or liquid, and this below this will always find solid. So when composition moving on this line, it will behave on the basis of liquid. That means which percentage of liquid is increasing. That means in this curve, another side is increasing, so that the curve is moving towards another side. The curve is moving towards another side because the percentage of another side is increasing. Here we have already 57 gram of dioxide and more is adding. That means the dioxide percentage will increase. That means that's why in solidus it will behave on the basis of solid, so it will move in this direction. So at this point, crystallization will cease. Why crystallization will cease? The simple thing is the amount of liquid you have taken, all is exhausted, all is crystallized. So that means from that point we don't have any liquid. That means that's why crystallization will cease here. The dioxide 82 anorthite 18 will get at the end. This is a equilibrium crystallization. This is a equilibrium crystallization. If you take any liquid, then which one will crystallize fast? From the figure, you will easily know that this when it will touch anorthite line, anorthite will crystallize. It will touch dioxide liquid, it will dioxide will crystallize. But it is depend upon the eutectic composition. The dioxide 58, anorthite 42. So any composition that is greater than dioxide 58 will crystallize dioxide fast. Any composition that is more than anorthite 42, then anorthite will crystallize fast. That depends upon the eutectic composition. If you have a composition dioxide 59, then anorthite 41, then dioxide will crystallize fast. If you have dioxide 57, anorthite 43, then anorthite will crystallize fast. So if you take any composition one of the phase will one of the component will crystallize fast. You take any composition except eutectic composition. If you take eutectic composition here, that is dioxide 58 anorthite 42 as a liquid, then for that composition only the crystallization begins with the simultaneous crystallization, and it doesn't have any path of crystallization. It will end at a particular point. Other cases we will find not. This is the crystallization path, but here it is the only crystallize at a point only, and it will crystallize begins with a simultaneous crystallization. But other cases, one component will crystallize, then they will come to eutectic point, then simultaneous crystallization will begin. So after tomorrow crystallization, we will get a solid. So you will take any composition, any liquid composition, below 1274, it is always in solid condition. You will take any composition, irrespective of any composition. Always, if that composition is below eutectic temperature, it is in solid condition. Real solid condition, irrespective of any composition. All composition meaning all composition has a solid temperature is 1274. All composition. So if you take a composition in the solid field, if you take composition, the same composition will take. If you take a composition in the solid field, and will start to increase the temperature. Will start to increase the temperature. Then what will happen? So similarly, when unless until is achieve its melting temperature, it will not melt. जब तुम्हारे से melting temperature achieve ना कर सकते तो melt करिए. So for dioxide 82, anorthite 18, it is below 1274 degree. If you raise the temperature, so it will touch 1274 degree eventually. So you will take any solid here. You will take any solid in this region, irrespective of any composition, all will start to melt at 1274 degree. Irrespective of any composition, they all will start melting at 1274 degree. All. But which one will melt fast? If you are taking dioxide 82, anorthite 18, then which one will melt fast? Huh? Both will melt. Both will melt. So dioxide 82, anorthite 18. So you have taken this composition as a solid. So now we are increasing temperature. Now this composition reaches to dioxide, that reaches to 1274 degree. Then both will melt, and one of them will completely melt. One of them will completely melt. So when it touches dioxide 82, anorthite 18, when it touches this point, dioxide will partially crystallize, anorthite will completely crystallize. Sorry, melting. Dioxide will partially melt, anorthite will completely melt. Okay, because at this temperature actually dioxide was crystallized at this temperature only. When this temperature will reach, it will also completely melt in increasing temperature condition. So for any composition, melting will begin at 1274 degree. Okay. For any composition, the fast melt will form, that is equal to dioxide 58, anorthite 42. Any composition, for any composition, irrespective of any composition, the fast melt will form that has a composition of dioxide 58, anorthite 42. And depending upon the eutectic composition, so one of them will completely consume. So which has a lower value than the eutectic composition. So here anorthite has a lower value, so anorthite 18. So when it will reach the eutectic line, dioxide will partially melt, anorthite will completely melt. Then we will get a liquid. It has a composition of dioxide 58, anorthite 42. It will also melt isothermal. It will also melt isothermally. That means that this will start to melt, and it will melt isothermally up to a liquid composition dioxide 58, anorthite 42 will reach. So your liquid will be here. Liquid will be here. So now the composition reaches when 1274 degree. We have this situation: 43% liquid. That is, liquid has a composition of dioxide 58, anorthite 42, and 57% dioxide. So you will take any composition when it will reaches 1274 degree. That means it will produce this much of liquid, and liquid has a composition of eutectic composition. Any you can take any composition. You can take any composition. So when liquid is here, so we have 57% dioxide and we don't have any anorthite. Don't have any anorthite because at this line, one of the phase will consume or one of the component will completely melt. But it will remain in the system. That liquid is remain in the system. So here two things will happen. If it is a equilibrium melting, if it is a equilibrium melting, that means that the melt that is formed, it will be in the system. So as it is be in the system, it will affect dioxide. It will affect the dioxide melting temperature. So that means if you have 1274 degree, if you increase the temperature to 1280 degree, it will melt some of the dioxide. So that means from this point, it will follow this path. And at this point, you will get completely melted thing. So take dioxide 82, anorthite 18 amount of liquid. Then, then if you raising temperature, you will get that much of dioxide 82, anorthite 18. I mean, the path is just reverse the crystallization path. The equilibrium melting is just reverse of the equilibrium crystallization. So if at that point fractional melting occur, fractional melting rate. So fractional melting means the amount of melt will form, it will remove from the system. The amount of melt that will form, it will remove from the system. So that when at this point melt has 43% liquid and only 57% dioxide, that is only dioxide. So if you remove all the 43% of liquid, you will left with only dioxide. तो खाली रह जाओ कौन dioxide रह जाओ. Only dioxide. If you have only dioxide, then if you raise the temperature, suppose 1274 degree, if you raise 1280 degree, 1290, it will not melt because now it is a unicomponent thing. Now it is a pure dioxide or 100% dioxide. There is no one to affect its melting temperature. So that's why there will be no melting between 1274 to 1392 degree. What we call a melting gap. Melting gap. So, if you take any composition on this part, if it is a fractional melting, all will end at a 1392 degree. Samaswara melting could end up 1392 degree. If you take composition here, then all will melt, all will end at 1550. If it is a fractional melting, but if it is a equilibrium melting, it will end where the crystallization was made. So, crystallization starting, say jagare end up. But if it is a fractional melting, it will always end at the melting temperature of that dominant thing, जो कि depend upon the eutectic temperature, eutectic composition. So that is your equilibrium crystallization, the equilibrium melting and fractional melting. So fractional melting thing होगी कि because of removal of the liquid, you will have a pure phase. So that will create a melting gap. That is the significance of fractional melting. If you do fractional crystallization, then what will happen? If you do fractional crystallization, same the amount of solid that form or the early form solid, they will remove from the system. It's a different process we will study in diversity. So that means कि from this point to this point, there will be the amount of crystal will form. It will remove from the system. From this point to this point, That means this 57 dioxide, the 57% dioxide will not be here if it is a fractional crystallization. So that means कि from this point to this point, the amount of solid form will remove. But in case of eutectic, there is a thing कि the early form crystal they does not react with the melt. So the early form crystal they doesn't react with the melt. That means the early form crystal is magmatically dead. Magmatically dead. They doesn't contribute in further crystallization process. If you remove 57% of dioxide, then the crystallization process will not be affected. Crystallization process will not affected. Crystallization process रे किसी changes आसवन का crystallization behavior रे किसी changes आसवन है. Only the final composition will change. Only the final solid composition will change. Because if you are removing 57% of dioxide, that is from this point to this point, that means we will not get 82% of dioxide. बुझा ना बुझ पाना यदि अच्छा so 100 ग्राम 57 ग्राम 43 ग्राम लिक्विड यदि रिमूव कर दो जो 57 ग्राम सॉलिड ऑलरेडी बाहर कर दो फाइनली अब टाइम की 82 ग्राम so that means ki if you are removing that 57 of gram solid so only that 43 gram of liquid will give you final composition and when any composition reaches to eutectic, it always have a composition of dioxide 58 and oxide 48. So if you take any composition here, all will form a solid. They have a composition of 58 and oxide 42 if it is a fractional crystallization. यदि गोटे fractional crystallization होउछि माने तुम जे कोनोसी composition निया all will form a solid 58-42%. If it is a equilibrium crystallization, that depends upon the initial composition. So actually fractional crystallization doesn't have any crystallization process effect. It will not affect the process of crystallization in case of eutectic. Eutectic process of crystallization को behavior को कौन से thing रे affect करे ना. Only the fractional melting that affects the crystallization melting behavior. But in case of fractional crystallization, only the final solid composition will change. For only one, nah, initial final samara. So for only one composition, the fractional crystallization and equilibrium crystallization will be same. That is the eutectic composition. So if you are taking eutectic composition, the all will crystallize at a particular temperature, at a single temperature. So there will be no fractionation because after complete crystallization there will be no fractionation. There are also same for melting. They have same equilibrium melting and equilibrium crystallization, fractional melting, fractional crystallization. So the effect of pressure and or addition of water to a eutectic system. So what will happen if you add water to a eutectic magma or if you change the temperature of the eutectic magma? So the different component will respond to temperature pressure condition differently because there are different substances. Main thing with increase in pressure, melting temperature will increase. So pressure, melting temperature they are directly proportional to each other. That means if you change the pressure, melting temperature will increase. But different substance will respond to the pressure differently. That means in some cases the pressure, the melting temperature will rise quickly. In some cases it will rise less. So it depends on substance. What substance kete respond to pressure ko. Accordingly, it will the melting temperature will change. So in case of dioxide of anorthite, dioxide will respond to pressure more than anorthite. That means ki with the increase in pressure, the melting temperature of dioxide will change more than the anorthite. It will change more than the anorthite. So if we are changing the pressure from 1 atm to 1 GPa, then what will happen? Everything in the diagram will raise. Everything in the diagram will raise. The eutectic composition will change. Then more eutectic temperature will change and liquid or solid they all will raise. But the eutectic composition it will move towards the component which is responding to the temperature less. sorry, to the pressure less. It will shift towards the component which is responding to the pressure less, or it will move away from the component which is responding to the temperature, responding to the pressure more. So it is like raise করছন্তি eutectic composition shift হচ্ছে কোড এই direction. So to this direction it is changing. That means it is shifting away from dioxide or towards the another. The utility composition will shift towards other side if you change the pressure, and all the solidus line, liquidus line, all will raise. So body. So if you add water, then melting temperature will decrease. Melting temperature will decrease. So here there's the reverse thing. The component which will respond more to the water content, which will the melting temperature will decrease. In case of here anorthite, the melting temperature of anorthite will decrease more than diapside. So anorthite अधिक decrease करते than diapside. So utility composition will shift towards the component which is responding more to the water. It will move towards the composition which is responding more to the water. So that's why if you add water, then the utility composition will also shift towards anorthite. In all cases, you can say it is shift towards the anorthite. Explain you can explain like this. In case of pressure, which is responding more to the pressure, utility composition will shift away from that component. In case of water content, which is responding more to the water, utility composition will shift toward that component. And here everything will be lowered. That means solidus will lower, liquidus will lower, utility temperature will lower. Everything will be lowered due to addition of water. The addition of water is inversely proportional to the melting temperature. The more the temperature, the more the water will add, the melting temperature will decrease. So it is a bicomponent system. So two components, phosphorate and silica. Also phase diagram. All things are same to eutectic, but the difference will study here. It also has three for phase: liquid, liquid plus solid, then only solid. So phosphorate was they are in liquid condition on this field, that is liquid field. So you can take any composition here. On the liquid field, we're taking a composition A. So it will touch the liquidus here. From this point, it will start to crystallize, just like eutectic. Just like eutectic. When it will reach this point, that is peritectic. It is 1585, or in some book you will find 1557, 43, different temperatures are given. So when it is reaches at this peritectic point, so from this point to this point, suppose the sum of the phosphorite is crystallized. Like eutectic, one of the component will crystallize fast, the phosphorite will crystallize. When peritectic point reaches, unlike the eutectic, here the alliform crystal, they will react with the melt. Alliform crystal react with the melt. So but in case of eutectic, they are not reacting with the melt, either settle down or remain within the magma as dead thing. But here the alliform phosphorite, when reaches to a suitable temperature, that is a peritectic temperature, they will react with the magma. They will react with the magma. So phosphorite, that is for Mg2SiO4, react with SiO2 to produce 2MgSi, that is your instatate. तर फ्रैक्शनल ହେଇଯିବ ବି ତଥାପି କ୍ରିଷ୍ଟାଲାଇଜେସନ ବିହେଭିୟର ଉପରେ ଫରକ ପଡ଼ିବ ନାହିଁ। So it will produce enstatite. So a reaction will begin at the peritectic point. So when a reaction will begin, the reactant, so one of the reactants should be consumed. At the point the gote consume ହେଇନି. So the reaction will proceed up to that point when one of them will consume either SiO2 or Mg2 SiO2, either olivine or SiO2. So at this point, there will be reaction between Mg2 and SiO4. They will produce acetite. So until unless one of them is consumed, the crystallization, the reaction will progress or continue. ये गोटे consume हो. So which one will consume? That depends upon the amount of crystal of olivine and the SiO2 present in the melt. So if you calculate here, the percentage of solid or olivine that form from this point to this point, it will be more than SiO2 melt. It will be more than the SiO2 melt. So you can calculate here how much solid is formed here by taking this lever rule. Calculate कर दो out. Suppose हमें इतना नहीं जो 10%, let's take 10%. Better होगा ना. Initially we have got first rate 90 and तुम्हारा SiO2 कितने? SiO2 10 initial. So this is first rate 90, SiO2 10, and peritectic composition is how much? 35. First rate 65, SiO2 35. It is a peritectic composition. Okay. So this is your initial composition. So this line will be solid. This line will be liquid, solid. Calculate करो कितने phosphate solid bar and कितने SiO2 melt. Calculate करेंगे तो आवश्यकता भी नहीं देखा. From this line you can see this line is larger than this line, means solid percentage is greater than liquid percentage. Right, solid percentage is greater than liquid percentage. Then liquid also contain phosphate and silica. So if you take pure silica, then it will more or less, it will be less than the solid that form from this point to this point. So that means कि the kinetic solid produce हो, the amount of solid that will produce, it will react with the melt. So if the solid percentage of olivine that is formed, phosphate that is formed is greater than the SiO2 percentage in the melt, so obviously SiO2 will completely consume. And the amount of SiO2 present, that will all converted to enstatite. So what converted? So there will be no silica left within the melt. There will be no silica left within the melt. So that means crystallization cannot progress towards the SiO2. Cannot progress from this point. It cannot progress to this towards this SiO2 component, because for this A composition at peritectic point, all the SiO2 is consumed by olivine and all will convert it to acetite. Then there will be isothermal crystallization here. So rest of the phosphorite and the acetite, they all will crystallize, and at the end we will get phosphorite plus acetite, because we have solid phosphorite. It will react with melt SiO2. It will produce melt acetite, and that will crystallize there. Which is there now? Crystallize. Then there are also some of the phosphate remain in the melt, that also crystallize here. So all will crystallize, and at the end they all will crystallize at this temperature only, isothermally at the TT temperature, and at last we will get phosphate plus acetite, because all the silica they are consumed by phosphate. So that means कि what happening in the peritectic point, that will determine which side the crystallization will progress, and that depends upon the initial composition, initial liquid composition. So if you take another composition, suppose you are taking a composition B, it is just above the you take insertite point. It is just above the insertite point. That means it has a composition approximately 30. Insertite is not 30. Insertite, sorry. For its SiO2 is 30. Phosphate is 70. SiO2 is 30. At this point, we are taking this. So when crystallization will begin to the peritectic point, peritectic point has a composition of phosphorite 65, SiO2 34. Now you calculate ki how much solid is formed and how much liquid is left. Calculate करो देखा. So you calculate and you will find that the amount of solid form is equal to the amount of SiO2 liquid. Now calculate. For this composition, the percentage of olivine that forms from this point to this point, it will be equal to SiO2 percentage. That's why both will consume. That's why both will consume and they will be converted to ancetite. Finally, we will get only ancetite. Here the amount of phosphate that is formed will converted to all will converted to ancetite. All will converted to ancetite because the percentage of olivine crystal form and SiO2 they all will converted to they all will consume because they have equal amount. So they will consume and convert into ancetite only. So that is the composition. For that composition, you will get your ancetite point. It's 30%. Ancetite point is always at 30%. Peritectic in different group it is little different. But if you take another composition at this point, C point, now the amount of solid from this point to this point, from this point to this point, the amount of solid form that is olivine percentage, it will be lesser than SiO2. It will be lesser than SiO2. So that means all the olivine will consume. So at this peritectic point, now we have ancetite plus SiO2 melt. Here there will be no olivine. You can see olivine, ancetite and SiO2 melt, and at that temperature, these two will behave like eutectic. They will behave like eutectic. So from this point, one of the phase will first crystallize, that is ancetite, up to eutectic point, which is that you can say 46 SiO2 46%. Then from eutectic point, simultaneous crystallization will occur between ancetite and SiO2. Then you will get ancetite and quartz as the final solid. As the final solid. So from this point, this is our, from this line we can divide the figure into two parts in terms of final solid composition. If we are taking liquid composition on this side, the final solid composition will be phosphorite plus ancetite. If we are taking composition on this side, the final composition is ancetite and quartz. Taking composition on this point, there will be only ancetite. To take B platform just a B line tight na. If you just I got a point anka majre भी नहीं that will also तुम्हारा H plus quartz equal to quad rho, and up to तुम्हारा peritectic composition there will be reaction between olivine and quartz. So up to this temperature olivine will form. So at this temperature तुम्हारा olivine will form. Up to this temperature olivine will form. After that, if you take composition, liquid composition, they will start to form enstatite. There will be no formation of olivine beyond 80 temperature. There will be no formation of olivine beyond 80 temperature. Direct is pyrazine will form, because after olivine pyrazine will form. So direct pyrazine will form, and you will get pyrazine and enstatite as a final product. Here also same. If you take composition, silica will first form, then along with the eutectic point, simultaneous crystallization, then will at last will get solid enstatite plus quartz. So this is your equilibrium crystallization. This one equilibrium crystallization. So remember 3 points. Depending upon the composition, one is composition between phosphorate field and enstatite field. Then SiO2 will consume. On the enstatite point, both will consume. In between enstatite and peritectic, olivine will consume. And beyond peritectic, there will be no formation of olivine, so no reaction. Because composition will not follow the or not pass through the peritectic point. If you do fractional crystallization, then what will happen? Suppose from this point to this point, olivine is crystallizing. Then the amount of olivine formed from this point to this point will remove from the system. If that will remove from the system, then there will be no olivine left for reaction. So that means that there will be no reaction in the peritectic point, and always you will get a solid which consists of enstatite and quartz. Always. There will be no formation of phosphorite and enstatite here, because there will be no reaction. But enstatite before this point, enstatite will form only by reaction. After that, it will crystallize from the melt. That's why during fractional crystallization, there will be no reaction. And this part, it will follow the eutectic condition. It will follow the eutectic condition. But if you are considering peritectic condition, then during fractional crystallization there will be no reaction. So the liquid always get richer in SiO2 percent. And in case of fractional melting, it also gives a very unusual behavior. Like if you are melting phosphate and enstatite, you are melting phosphate and enstatite, you will get phosphate and silica. You will get phosphate and silica. So this type of melting is called as incongruent melting. Incongruent. This type of melting is called as what? Incongruent melting, where the solid composition after melting, the melt composition and solid composition will be different. In case of eutectic, if you melt dioxide anoxide, you will get dioxide anoxide. That is congruent melting. Here it is incongruent. If you melt phosphate and enstatite, you will get phosphate silica. So similar thing can happen here with phosphate enstatite. When it will melt, so all the enstatite that is formed here, they all will be melted. Only phosphate will be left. So it will remove, and same behavior will be shown here during fractional melting. But unusual thing is key, you will find a liquid that is different than the solid composition. বুঝতে পারছো? Understood? যদি ডাউট আছে তাহলে ask. तुम्हारा solid solution जोतरे की there is no eutectic or peritectic point here. There is no point when they will simultaneously crystallize. So here they will always form a solid which is a mixture of both components. Which is a mixture of both components. So here you can actually call it as liquidus and this is solidus because beyond this point will always get liquid and below this point will always get solid. So in case of eutectic, that is actually not called as solidus, liquidus. So here it is, you can say liquidus and solidus. So albite and anorthite. Albite has a melting temperature of 1118 degree, otherwise 1120. Anorthite has 1553. So similarly, in liquid field, we will take a composition. So same principle, presence of one component will affect the other. So when it will touch the liquidus, it will start to crystallize. So when it will reach this point, it will start to crystallize at this point. So we'll take a point just below that, this point. So from this point, liquid will start to crystallize. So the composition of liquid will change. So it will produce a solid that consists of albite and anorthite, and liquid also consists of albite and anorthite. But in case of eutectic peritectic, the solid was formed only consists of a single component initial. Then after eutectic or peritectic point, there will be simultaneous condition. But here, the solid that will form always contain both albite and anorthite, and also the liquid also contain both albite and anorthite. So at a particular point, this line to the FCSI it will give liquid composition, and this line to the FCSI it will give solid composition. So the perpendicular line from the solidus they will give solid composition. Perpendicular line from the liquidus they will give liquid composition. And for a particular liquid, how much amount of solid or what percentage of solid will form, that will given by this tie line. Suppose our liquid is here, then what composition of solid it is forming, you can draw a tie line to the solidus. So for this liquid composition, it is producing this much of solid composition. There is more albite 28, anorthite 72, for liquid composition, albite 67, anorthite 33. Initially, the initial composition is albite 58, anorthite 42. Initial composition. So now it will crystallize like this. So with falling temperature, crystallization progress, liquid will convert to plagioclase. The amount of solid that form here, suppose this plagioclase, it will exchange or react with or melt to produce another composition of plagioclase. Plagioclase 1 suppose plus melt 1. This is a reaction is going on here. The amount of the plagioclase produced, then again it will exchange with the melt. Again the plagioclase will modify and the melt will modify. So with progressive crystallization, the percentage of calcium or percentage of you can say anorthite, it will decrease in both liquid and solid. Percentage of anorthite, it will always increase in both solid and liquid. And here always crystallization progresses from anorthite to albite. Always. That is the temperature falling condition. If anything that progresses from albite to anorthite, that means it is a melting condition. Always anorthite to albite. So gradually that crystallization will progress like this. until unless ki the amount of liquid you have taken, the amount of liquid initially that much amount of solid you will get. But here ki there is no particular temperature where it will end. So always there are some melt may left here. इसलिए melt मेरे में रह ही जाए. That means कि particular temperature जो all melt should consume or something, that is not the condition here. So initially हमें जहाँ composition नहीं था, the amount of percentage of melt you have taken initially, when we'll get that much of solid, then crystallization will end. The path of the liquid is here and path of the solid is here. In both cases you can see they are going like this. Percentage of calcium is decreasing, percentage of sodium is increasing in both solid and liquid. This is equilibrium crystallization. Just the reverse is equilibrium melting. Exact reverse is equilibrium melting. So gradually it will melt, produce plasmacles, again melt, produce plasmacles. But what happens in case of fractional crystallization and fractional melting? Suppose here at this point it is crystallizing from this point to this point. We have 97% of solid plasmacles formed. If it is a fractional crystallization, that means we don't have that 97% of plasmacles solid here. It will be removed from the melt. Now we have that 3% of liquid. Yes, 3% of liquid, which has a composition you can say albite 92, anorthite 8. Albite 92, anorthite 8. So that 3% it is not key. It is not the condition key that will only crystallize at that point. It may be come to 2%, maybe 1%. So that means ki we don't have a definite composition which will define how much substance will form in a fractional melting condition. In case of Eutectic, we can say that this is the condition. Here is the last temperature for crystallization. So that means ki at that temperature the amount of solid form, that will be case of fractional crystallization. But here that is not the case. We cannot say when we cannot say the temperature when the crystallization will end. At what point it will end. Who point end होगा हम कहीं पर 3% to 2%. That means कि in case of fractional crystallization, we always get a solid that is very richer in sodium content. That is very richer in sodium content. Sometimes you will get 100% of albite also. Sometimes you will get 100% of albite. This is a case of fractional crystallization. Similar thing also happen in case of fractional melting. You will get always a melt that is always richer in calcium component. That is always richer in calcium component, and we might get 100% of another thing. I would say when a liquid and solid are coexisting with each other, that is at the end of a tie line. At the end of the tie line, solid and liquid they will coexist with each other. They are in equilibrium with each other. In that condition, remember, the solid has more calcium percentage than liquid. So when a solid and liquid are coexisting with each other, the solid has more calcium percentage than liquid. And progressive crystallization to make calcium by sodium ratio determine the calcium by sodium ratio will decrease or sodium by calcium ratio will increase. Those are the things. If there is in equilibrium crystallization, the in equilibrium way, but sudden cooling, if this thing will happen, it will produce zoning. It is the characteristic of solid solution. Zoning. Maybe early form calcium They are surrounded by sodium. While from calcium, they will be surrounded by sodium. Initially, there will be some plagioclase crystal, like calcium rich crystal. They will be surrounded by sodium rich crystal. That is your tuning condition. In equilibrium condition, but sudden cooling condition.